Hi guys, we'll give it just a sec to let other people show up. How's everybody doing today? Okay, we're actually going to be starting chapter 2.3 today. 2.3 is taking our ideas about matrices and then applying them to transformations. And then don't worry about, having time to practice this stuff. We actually have time to practice this material in our schedule. Yeah, I'm pretty tired too. Okay, so let's go ahead and start talking about 2.3. It's called linear transformations. And we're going to use matrices, matrix representation, to do that. Okay. I guess I'll set with that. All right, so let's think about, for example, if I've got, I've got A be a matrix. It's a 2 by 3 matrix. And let's say, for example, I'm going to define A as being these elements here. 2 by 3, it's got 2 rows and 3 columns. Okay, so remember how we defined our dimensions on a matrix. So if I want to do this A times X, right, where I say X is equal to three-dimensional vector with X, Y, and Z components. This is a 3-dimensional input, say for example. And then A is some kind of a matrix representing like what I want to do with that. So let's go ahead and multiply it out. Let's see if we can do this. So this is, if I do A times X, it's going to look like this: 1, 3, 0, 1, minus 1, 2. And then X is going to look like X, Y, Z. So we take our vector and we write it as a column vector. Okay, so I'm gonna write as a column what we call, oops, I can spell column vector. Okay, where I take my components of my vector and I turn it into a 3-row, 1-column vector. Okay, now if I've got a 2 by 3 and this is a 3 by 1, right, my inner dimensions for multiplying are going to match, and my output is going to be a 2 by 1 output. Okay, so 2-row, going to be 2-row, and then 1-column output. So what this is going to look like is, remember how we do this. We say this is going to look like my first row times my first column. So it's going to be 1 times X plus 0 times Y plus a minus 1 times Z. My second row times my first column, 3X plus 1 times Y plus 2 times Z. And if I put these together, it's going to look like X minus Z, 3X plus Y plus 2Z. Okay, so this is the important thing. Now I can take this, right? This is in terms of X and Y and Z, and I can put this back into what looks like vector form. Right? And I now have a 2-dimensional output. So I've gone from a 3-dimensional input, X, Y, Z, to a 2-dimensional, I've got this term and this term, output. Okay, so I've done a transformation, right? This multiplying by this matrix has transformed my input from 3 dimensions to 2 dimensions. So this whole thing, this we're going to say, this is going to define a function. We're going to say f of x equals a times x bar. Okay, and this function basically transforms from 3 dimensions to 2 dimensions, right? This is how we say this is a transformation, right, from 3 dimensions to 2 dimensions. Okay, so for example, on my function, if I take as input I'm going to go 1, 2, 3, right? So 1, 2, 3, I plug that in, right, for x, y, z, and what I get out is going to look like 1 minus 3, so I'm plugging it into here. 3 times 1 plus 2 times 3, okay? So this is going to be minus 2, comma 11. Oops, sorry, you can see that. So I've taken in as input 1, 2, 3, and I have as output minus 2, comma 11. So I've gone from 3 dimensions to 2 dimensions, okay? And we've done that by multiplying by a matrix. We've transformed, okay? This is part of what we're going to be talking about today when we talk about transformations. So transformations can not just rotate things, reflect things, move things around, but it can actually take things from one dimension and put it in and basically transform it to a different dimension, okay? When we talk about things, we need to think about whether or not we're talking about a linear map versus nonlinear maps, okay? There are different types of nonlinear maps. We'll talk about those in subsequent sections, but I'm gonna throw some out today. So we say a linear map. We like linear maps because they're very straightforward. So linear map, we'll say, is a transform from the mth dimension to the nth dimension. We're going to say this is going to correspond to a unique n by m matrix, right? So my input dimension was m, my output dimension is n. The matrix that helps me do that transform from m to n dimensions is an n by m matrix. Okay, so I can say if m is the matrix of transformation, say T, R, M, R, N, all real numbers, right? It's all real numbers. Then the jth column of M is T, E hat sub j, and we're going to talk about what all this means here, where E hat sub j is the jth basis vector of our sub. And remember your basis vectors? This was 1, 0, 0, 0, 1, oops, 0, and so on and so forth, right? So in 3 dimensions, I would have x, y, and z. You know, so if I've got my jth basis vector, it's going to depend on what dimension I'm in, right? So if I've got this, since it's 3 dimensions, then my basis vectors they look like this, okay? This would be I, J, and K. Remember we talked about those. We use those to help us do cross products and stuff. And now why I'm talking about this is because we're going to use our basis vectors to help us come up with basically a matrix of transformation. Okay, so let's talk. We're going to take a step back. I'm pulling out my lecture examples for 2.3. This is going to be you know, a lot of stuff. There's like examples that we're going to put a lot of things on here, so that this will be a really important lecture example thing to have. I'll scan this in later and put up the solutions. So if C is, right, so this, how many rows? We've got 1, 2, 3, 4. So this is a 4 by 2. So 4 rows and 2 columns. And our input is y1, y2. Okay, so this is a 2-dimensional input. So this is going to be 4 by 2. I'm going to write this as y1, y2. So this is a 2 by 1 matrix. So my inner dimensions match. My outer dimensions are 4 to 1. So I'm taking a 2-dimensional input, and I'm going to basically be coming up with a 4-dimensional output. So this transform here, our H, goes from 2 dimensions to 4 dimensions. This is how we want to think about it. So if I do C times Y, I'm going to set this up. 5, 1, minus 7, 0, minus 3, 0, 4, minus 2, and then Y1, Y2. Okay. So remember our matrix multiplication, first row, first column, it looks like it's going to go 5y1 minus 3y2. Second row, first column, 1 times y1 minus 0 times y2. Third row, first column, minus 7y1 plus 4 times y2. This was a minus here because of the minus 3. So it was a plus minus 3. 0, this row here times this column. 0 times y1 is 0, plus a minus 2 times y2. Okay, so we've gone from inputs y1, y2 to these outputs. Oops, that's a y1. 5y1 minus 3y2. 1, 2, 3, 4. So 2-dimensional input to a 4-dimensional output. Okay, so then I can say cy. It's going to look like 5y1 minus 3y2, comma, y1, comma, minus 7y1 plus 4y2, comma, minus 2y2. I ran out of space. That's why I didn't write it on the same line. Okay. Right, so there's 1, 2, 3, 4 dimensions on our output. Okay. Just an example of a transformation for that. Okay, so how do we tell if something is linear? If a transform is linear or not? Okay, because there are different types of nonlinear transforms. So for a linear transform, it has to satisfy two different things. Linear transform. So we say it's a function t Rn to Rm, and it satisfies these two different qualities. So the first one is, I'm going to write it out first in math and then we'll talk about it. Okay, so to be linear, right, we say that our transformation has to satisfy the addition property, which is, I can say the transformation of x plus y together is equal to the transformation of x plus the transformation of y. Multiplication property says the transformation of a is just like some constant, right? A is equal to a constant. Transformation of a times x is equal to a times the transformation of x. So these are two things that we need to check when we're checking to see if a transformation is going to be linear or not. Okay, so if it satisfies both of these, then it's considered linear. Okay, we can say x and y, they're real, these are vectors, okay, on our input side, on our inputs, and then a is a real number. This is a scalar. It's a constant term. Okay, so that's linear. One of the nonlinear forms is called affine. We're going to spend some time with that later in a later section. An affine transformation contains a linear portion and a nonlinear portion. Let's say, I always think y equals mx plus b. Okay, so y equals mx is our linear portion, right? And then the plus b is the affine portion. Okay, this is how I remember things. So I say my affine transformation, I'm going to go from the nth dimension to the mth dimension. And this transformation looks like I take in an input x, and I have my transformation on x plus, I have some, basically, you know, I'm displacing it by some value. This is a vector. Okay, so that's our what we call an affine transformation. Now there are many other types of nonlinear transformations, like, you know, parabolas are nonlinear, cubic equations are nonlinear, things where we have our variables being multiplied together. Those are considered nonlinear as well. But basically, what we need to do when we go to check to see if something is linear or not, how we do that is, oops, roll this up, that there. How we do this is we have to look at each term of the component, this terms of the components of our output, So if each term is a number, just a scalar number, times one of the components, like x, y, or z, then it's linear. Okay, so if it's like 3 times x, right, that's linear. Or if it's like a 3 times x plus 2 times y, those are linear. Okay, we'll do some examples on our example sheet so that you can see what's linear, what's affine, what's other types of nonlinear. So I'm looking at my lecture examples page. Sorry, my papers are moving all over the place here. My lecture examples page here, example 2, we're going to look at each of these transformations. So I take in an x, y, z, and I do something to it, and I get this out. I get 3x minus y, 3z, 0, z minus 2x as my output. So I look at each component and I say, do I have a constant term times my variable, and then some linear combination of my stuff. So I've got 3x minus y, 3z, everything's being multiplied by a number, and then I'm combining things. So I've got a number times the component, and I've got a linear combination of terms. That means I'm adding and subtracting, right, my terms. So therefore, I can say this is a linear. I just could have eyeballing it. It's a linear. Okay, I'm going to look at this one here. So I've got 3x minus y, 3z plus 2. Oh, looks like, wait, did I just repeat? Oh yeah, 3z plus 2, 0, and z minus 2x. Okay, so now I have to look. So I've got 3x minus y. This is good. 3z plus 2. I've got this plus 2. This plus 2 hanging out there is kind of throwing me off. It makes me think of y equals mx plus b, right? So these are fine because I've got a linear combination of my components, of my terms, right? But I've got this 2 hanging out there. So 3z plus 2, this term here, that plus 2, throws it off to make it like it's a linear plus a transformation, like a translation. So this is an affine. Okay, so this is considered non-linear. It's an affine translation. Okay. Part C, let me look. 3x minus y, 3 times x times z. 3 times x times z. The other ones are the same as before. 3 times x times z, 3 times x times z, right? So this is like saying 3 times x, x squared, right, is a parabola. I'm multiplying 2 major components together. So therefore, this thing is nonlinear. It's not affine even, it's just nonlinear. Okay. All right, so now our big question now is, if I've got some kind of function, I'll work it through with an example. If I've got some kind of function, right, I want to be able to take a look at how do I go from a function, its output, to the matrix of transformation that I got, right? So I want to be able to look at things. So let's think about how I can do that. See. Okay. So first, let me write down like how we can think about it. So Okay, so if we're given the output, how do we come up with the transformation matrix that got us there, right? So I want to be able to think about that. So we think we've got this function here, f of x, y, 2x plus y, y, and x minus 3y, okay? So basically, my inputs are 2 dimensions. We've got 1, 2, 3, and a 3-dimensional output, right? So my function is to transform from 2 dimensions to 3 dimensions, right? So I've got a 3-dimensional output. So I need to be able to think about my function as being a times my input. So this is like my input here. Okay. So that means, right, that because I'm going from, like, say, 2 to 3, that means A will be a 3 by 2 dimensional matrix, right? Because my input, think about what it's going to be. So my input is going to be x and y, right? And then I have to be able, this is a 2 by 1. And then I have to have my inner dimensions agree. So this has to be 2 by, but I'm going to a 3-dimensional output. So 3 is going to be there. So my 1, 2, 3, 1, 2, 3, 1, 2, 3. So I've got 3 dimensions, right, that I need to take into account on my A. So this is my A, this is my X. So I'm kind of thinking about how do I set up my A matrix in order to handle that. Okay. So now I'm going to write it like this. I'm going to start spelling it out. So A11, A12. Oh, sorry, I should have 3 by 3. This is bad. Sorry about that. Let me erase that part. Did a 3 by 3. There. Okay. So A11, A12, A21, A22, A31, A32, and I have X and Y. So when I do my multiplication on my matrix, right, it's going to come out like A11X plus A12Y, A21X plus A22Y, A31X plus A32Y. This is my output. Okay. So remember, this is our 3 by 2, and this is our 2 by 1. Okay, so our answer is going to be a 3 by 1. Okay, we can see that in our multiplication here. Okay, so now I can use our unit basis vectors to help us figure out what A is. Okay, so my unit basis vector, let's see, I need another piece of paper. So I'm going to use my unit basis vectors for that. So this is example 3. Continuing. Okay, so let's use our unit basis vectors to help us figure that out. So let's remember what they are. So the first one is, I'm going to say, I'm going to let my x bar equal to my first unit basis vector. This is I, right? Oops, I. Okay, my first unit basis vector, I'm going to try to figure out my, my x, essentially. So I'm going to go f1, 0 is going to equal to 2x plus y. This is our answer here, is 2x plus y, y, x minus 3y. So this is, I'm taking my, this is a11x plus a12y, a21x plus a22y, a31x plus a32y. Okay, so if I plug in, right, 1 for x and 0 for y, then what do I get? And I can use that to help me figure things out, right? So let's go ahead and do that. So if I plug in, so I'm going to say this is going to be A11, A12, A21, A22, A31, A32 times 1, 0. So what do I get, right? I'm going to get, this is equal to 2 times 1 plus 0. So I'm taking in these values here. 2 times, I'm going to plug in 1 for x and 0 for y, 0. And then 1 minus 3 times 0. Okay, so basically when I do out the multiplication on here, right, this is going to be A11x plus 0. This is going to be A21, and this is equal to 2. A21 is equal to 0. A31 is equal to 1 right here, because this is a 0. Okay, so that means then, right, that my first column, this is my first column in my A matrix. Okay, I know it seems a little confusing. We're kind of working our way through, but we're using our basis vectors to help us solve this equation here. Okay, to be able to solve for what A11, A23. It basically, this whole column is going to go away because my y is equal to 0. Okay, so I'm essentially setting, right, A11 is going to equal to 2. A21 is going to equal to, equal to 0. And then A31 is going to equal to 1. So now we need to do this with our other basis vector, right? This is our J. So I'm going to plug that in to my, I'm going to plug this into my function here. And I'm going to do the same thing that I did before. So this is A11, A12, A21, A22, A31, A32. This goes 0 to 1. Okay, and I'm plugging this into here. So this is going to be 2x plus y, y, x minus 3y. So if I plug in 0 for x and 1 for y, right, I'm going to get 2 times 0 plus 1, 1, 0 minus 3 times 1. Okay, which is going to give me A1. So A12 is going to equal to 1 right here. A22 is going to equal to 1. A32 is going to equal to minus 3. So this is our second column. I'm sorry, you can see that second column in our matrix A. So then I can put this all together and then say A, my first column, 2, 0, 1. My second column, 1, 1, minus 3. If I multiply A by x, y, I'm going to get out the what I was given here. This was, I was told this was the output, and so this is going to give me my output. So this is how I backtrack to find the matrix of transformation. Okay. I know it's a lot to take in. There's a lot going on here. We're just going to work it through. I'll scan these in later so that you have them. Okay. All right. So some things I want to mention too, that any combination of two linear maps is also a linear map. Okay, so if I know that I'm dealing with, I'm going to combine two different linear maps, I know the result is going to be a linear map. So this is also like the composition of that. So let's just talk about what types of linear maps that we have. So linear maps that we have are our identity map. That's basically like if I multiply it by the identity matrix, it doesn't change anything. Okay, we've got our reflection map. We're going to actually go into details on these here. Our rotation map and our projection map. These are all examples of linear maps. Okay, so nonlinear types of maps. We have a translation, right? This is it's an affine where I say I'm gonna, move something over and then up. Okay, I'm translating it in its position. Okay, so this is like, this is our affine translation. Okay. Also, other examples of nonlinear are things like x squared, xyz, xz, and so on and so forth, where we're multiplying our basically our input components together. Yeah, you can imagine this is a parabola, right? That's a nonlinear function there. All right, so I'm putting these into the, we're going to talk about our maps for reflection, rotation, and projection, but I'm putting them into the examples, lecture examples, so that you actually, when we scan this in, you'll actually have them out. So it's kind of like a lecture notes thing too. So let's talk about example 4. 4a is we've got this transformation we want to come up with. What's the reflection over the x-axis is given by what? So to derive this, I think about, here's my x, here's my y. Okay, so let's say I've got this point in space, it's an xy, and I want to like reflect it over the x-axis. So this is the axis that I'm looking at right here. I want to reflect it over this axis right here, x. Okay, so if I'm going to reflect it over the axis, I'm right here. Okay, so where have I gone? So like I'm right down there. So I haven't changed anywhere in my x. I've still gone the same distance out in the x. The y now, it's the same value, but it's negative. I've gone over into the negative negative direction. So our reflection across the x-axis we call REF sub x, like because I'm reflecting across the x-axis. So how I think about this is like this, right? Then I would derive my unit basis vectors using my unit basis vectors to come up with the matrix, but I'm not going to go through all those steps. So I haven't changed anything in the x direction. And in my y, I've made my y negative. So you can imagine that if I were to multiply this by an x and a y, what I'm going to get is, this is a 2 by 2, this is a 2 by 1, so my answer is going to be 2 by 1. This is going to be x, negative y. Okay. We're applying it to the coordinate x, y. Okay, so this is our reflection matrix here, right? 1, 0, 0, minus 1. When we reflect over the x-axis. Okay. Now, when I think about, I'm going to rotate by 90 degrees. We're going to first talk about 90 degrees, and then we'll talk about rotating by any angle. So when I rotate by 90 degrees, right, what happens is like this. So you can think about it, where if I'm, right, if I've got a point here, so this is my 1, 0, this is my 0, 1. So my 1, 0, by rotating by 90 degrees becomes 0, 1, right? And then if I'm here at 1, 0, and I rotate by 90 degrees, I'm here at minus 1, comma 0. Okay, so this is like, right, because I'm on the x and the y axis. So this is how I'm thinking about it. So if I rotate by 90 degrees, what happens, right? So if I take in an x, y point, what I'm going to get out is minus yx. Okay, so then we say our rotation by 90 degrees is equal to 0, 1, minus 1, 0. Okay, right, and if I apply this to the coordinate x, y, okay, what happens? First row, first column. So I'm going to get, right, I'm going to get, oops, minus y. So 0 times x plus a minus times y. And then I'm going to get x plus a 0 times y. Okay. But this right here is my rotation by 90 degrees. Okay. We start off with 90 because it's a pretty common thing, but really what we're going to do is we're going to make it generic. By talking about rotating, and this is rotating counterclockwise, rotating by any angle. So the next example is rotation by any angle. Okay, so let's think about what's happening here. So here's my x, here's my y. So if I start here at this point, right, and I'm going to rotate by my angle theta. Oops, you can see it. Rotate by my angle theta. So then I'm going to end up at this spot right here. And basically what's happening is, right, this spot, because of right angle trigonometry, this spot is given by cosine of theta, and this spot is given by sine of theta. And this is from our right triangle trigonometry. Okay, I'll write that down in a little different color. So our x direction is represented by cosine of theta. Our y direction is represented by sine of theta. That's our unit circle. And right angle. Okay, this is the SOHCAHTOA stuff that we talked about a while ago. All right, so now I'm rotating by any particular angle. So I can think about it like that. This is if I go right here, I'm using my unit basis vector with the I. If I start off with my unit basis vector with J, if I start, this is Y, and then I go a particular angle, right? So I'm going this way and I'm going to finish here at this spot here. What happens is I'm at minus the sine and the cosine is how we think about it. And this is, I'm using unit basis vectors in order to come up with it. I'm not showing you all the derivation on it, but this is, then here we'll write it out. So this is x bar equals 0, 1. Rotation by any angle theta applied to 0, 1 is going to give us minus the cosine of theta. Okay, so now we can apply these. This is our first column. So our rotation by any angle is going to be cosine of theta, sine of theta. And our second column is going to be minus the sine of theta, cosine of theta. Okay. We're going to see example 7 takes this rotation matrix and we're going to apply it to a particular point. Okay. So let's scroll up just a little bit. Let's plot this out. 1, 2. So I've got the point 2, 3, and I want to rotate it by 30 degrees. And I want to find out like what's that point where I'm going to end up. So I'm rotating this point 2, 3 by 30 degrees. Okay, and I want to see what's going to happen. So what I need to do is I'm going to say my rotation by 30 degrees is going to be cosine of 30, sine of 30, minus the sine of 30, cosine of 30. Okay, and I'm going to apply that to the point 2, 3. Cosine of 30 and sine of 30, these are things on my calculator. I plug them in. I'm in degree mode because I'm working with degrees here. So when I plug that into my calculator, I'm going to get cosine of 30 is 0.866. You can go 3 places after the decimal. Sine of 30 is 0.5 minus the sine of 30 minus 0.5 and then cosine of 30 again. And this is multiplied by the 0.23. So this is how I'm transforming, how I'm moving. I'm rotating that 0.23 by 30 degrees to a different coordinate. So now when I do this, my first row, first column, I multiply. This is going to look like 2 times 0.866 plus 3 times minus 0.5. And then my next one is 0.5 times 2 plus 866 times 3. And I'm going to do this on my calculator. I add it up, and I'm going to get, this is going to give me 0.232 and 3.598, which is the point 0.232, comma 3.598. So I'm looking at this new rotation is 0.232. So I'm like right here, and I've gone up roughly here. So my point that I'm ending, so this is a 30-degree angle right there. I kind of imagine that. Let's draw that out in orange. Okay. So that's how we think of it. This is where we started, 2, 3. And this is our end point, 2, 3, and 3 point, roughly. Whew, a lot of stuff, right? That's why we're putting it in the lecture examples so that you can have a copy of it. Okay. How's everybody doing? I think I'll do one more example, the next set here, and then we'll take a break and maybe go back to the classwork for chapter 2.2 and just practice some of those pieces there. So we're looking at coming up with the transformation matrix of rotating across the line that is at a given angle theta to the x-axis. Actually, did I say rotating? This should be reflection, sorry. Reflection across a line that's at a given angle. So what that means is, right, I've got my x and y axis, and then, you know, here's some line, which we're going to represent our parameter by the symbol all real numbers, and it's and I'll say here's the line that is making an angle theta with the x-axis, and I've got this point xy, and I want to reflect it across this line here. So I'll call this x prime, y prime. Right, so I'm reflecting it across this line that's making an angle with the x-axis. So the steps that we need to do, sounds really complex when I'm going to write out the steps, but it's not so bad. So what I need to do is I have to rotate the plane to line up with the line that we're calling our theta. So I'm going to take my plane and I'm going to shift it this way. Okay. Then I'm going to reflect across our new x-axis, right? So I take this plane, I bring it up to here, and I'm going to reflect across the x-axis, and then I'm going to bring the plane back. Back to original, which means I'm rotating back to the back to where I was. So this is what we call a composite transformation, where I'm doing bam, 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 3 transformations all in a row, and I can actually multiply all those matrices together and come up with one matrix that does this. Because if I think I'm going to be reflecting across the line a lot, right, this particular line, then I'm just going to come up with one matrix to represent that and then use it over and over again. So let's call this reflection across theta. It's going to look like our composite is going to be, right? Let me write it out. Okay, so what's going to happen is, right, I'm going to and I'm going to apply this to my x and my y. So I first rotate to bring the plane up. I reflect across the x-axis, and then I rotate it back. Okay, this is like we kind of read it in this direction right here. Okay, so then the reflection across the line looks like this: cosine of theta, sine of theta, minus the sine of theta, cosine of theta. This is our reflection by an angle. Or I'm sorry, rotation by an angle. Reflection across the x-axis was this matrix. Remember, we did that before. And now I'm going to plug in a minus theta into each of these things here. So when I plug in a minus theta, cosine of a minus theta is cosine of theta. Sine of a minus theta is minus the sine of theta, which makes this positive sine of theta. And then this is, whoops, cosine of theta. Okay, so whatever angle my line is making with the axis, I'm going to plug that into here. Okay, so now I'm going to multiply these matrices together. Okay, and it doesn't matter if I multiply these two and then that one, or these two and then that one. It's, you know, because the dimensions will work out either way. You're going to come up with the same thing. So I'll just multiply these two first and then that one. So the intermediate step. Right, so I multiply these two together. I'm going to get cosine of theta, sine of theta, sine of theta minus the sine of theta. That's when I multiply these two together, I get this one. This is theta, and that's a theta. And then multiplying these two together and summing up is going to give me cosine squared of theta minus sine squared of theta, 2 sine of theta, cosine of theta, sine of theta, cosine of theta, sine squared of theta minus cosine squared of theta. Now I'm deriving all this for you. In the end, you're just going to have like one matrix. This thing here, I'm going to combine Trig Identities. Combine. So these are all based on trig identities. So the trig identities used were sine of 2 theta equals 2 sine of theta cosine of theta, and then cosine of 2 theta equals cosine squared of theta minus sine squared of theta. So these are the ones that I used here to simplify this. So now my reflection across some line that's making an angle with the axis going to be the cosine of 2 theta, sine of 2 theta, sine of 2 theta minus the cosine of 2 theta. And this is the one that you need. I spent a lot of time deriving it. You can just, when you go to use this to rotate, to reflect across a line that's making an angle with the axis, this is the matrix that you're going to use. You don't have to derive it from scratch every time, okay? So this is the matrix that we'll use. So let's apply it to this line here, the line y equals x. All right, so the line y equals x, I need to think about that one. So I'm given this, so this is 1, 2, this is 1, 2, and so on and so forth. So y equals x means it's just this really straight line. Y equals x. And I have to figure out what theta is, right? So I'm going to make a right triangle, okay? And I've gone over to, this right triangle looks like, here's theta, here's 2, and here's 2. So I basically took this out of context and oops, sorry, you can't see it, and I drew it there. So if I want to figure out what theta is, that's my whole point, right? So then when I look at this, I can do sine or cosine, but I have to figure out what that, hypotenuse is, but I can do tangent. Theta is opposite over adjacent, which is equal to 1. So the angle, I'm going to do this is also a function of my calculator, so that inverse tangent, and my theta equals 45 degrees. So I found my angle that my line is making with my, my axis. So that's the angle that I'm going to plug into here. So I'm going to go reflection across an angle, a line that's at an angle 45 degrees is going to look like cosine of 2 times 45, sine of 2 times 45, sine of 2 times 45, minus the cosine of 2 times 45. Make sure you multiply by 2 first before you take that. Okay, so cosine of 2 times 45 is 90. Cosine of 90 degrees is equal to 0. Sine of 90 degrees is equal to 1, and then 0. And I'm going to apply this to the point 2, 3. Right, so I've gone 2, 3. This is the point that I'm trying to work with, right? So this is 3. Okay, so I want to reflect it across that line. So I'm going to do my matrix multiplication. So 0 times 2 plus 1 times 3. 0 times 1 plus 1 times 2 plus 0 times 3. So 0.23 reflected across line y equals x is 0.3, 2. So let's write that down. So 3, 2, right there. When you graph it out, it should be in the right ballpark. I mean, I know I'm not a great artist, right, when I draw these things out, but I can at least see that it's in the right ballpark. It's doing basically the right thing, okay? If when I got this, if I got something that was in a different quadrant, it's like way over here somewhere or down here or whatever, I think, oh, maybe I did something wrong. So I go back. So the graph, I'm not going to grade you on the graph, but it will help you think about, are you doing this thing right, okay? So this is what we're trying to do here, okay? So I'll stop here for now because I've been talking a lot this morning, and I'll scan in this stuff here so you have it to take a look at, and then we'll finish up 2.3 on Monday and then maybe start 2.4. But let's go back to some of the classwork that we had on 2.2, And I'll just start working through some of the classwork problems that we had on 2.2. This was like combining matrices, different things. Can I do matrix multiplication, you know, stuff like that. And I'll just start working through those problems here on the screen. Okay. I know this is a lot to take in, but you know, give yourself time to let it sink in so you can think about it. Okay, so I'm looking at classwork for 2.2, and I'm going to do part one. Part one right now.
How you guys doing? Do you have any questions on what I've just been doing on the part one? I'm going to start on part two. I'm actually going to come back to it. We're doing this in a later chapter. We'll come back to this page here because it's about inverses, and there's actually a whole chapter section devoted to inverses. So we're going to come back to this page here. I'll post the lecture video a little bit later today so you guys can see it. And I have office hours today if you guys have any questions. Take it easy, guys. Have a great day.